Dichotomy for key agreement protocols. Yitzhak Heitner, Computations, Iran Orly, Ronen Shaltil, and Jad Tilbach, and Jad will give the talk.
Okay, thank you. So let's talk a little bit about our setup. And we're going to talk, our focus is two-party protocols. And specifically, we're going to talk about no input, single output protocols. Now, by this, we mean that we have, say, two parties A and B. They receive some security parameter K. The parties interact. And as a result, we get a transcript T that is visible to anyone. Now, at the end of the protocol, each party will output one bit. A will output X, and Bob will output Y. Now, this is a very standard natural setup. And perhaps the most known example for such protocols is key agreement protocols. And this is quite relevant to our discussion today. Okay? So let me define this. We say that A and B are a key agreement if they satisfy two properties. The first is agreement. And by this, we mean that X and Y are almost always the same. And the second is secrecy. Now, here we mean that any eavesdropper E that is polynomially bounded, its ability to predict X given T is at most half some plus some negligible function. Now, I want to stop here for a second because the next point is quite important. What does an eavesdropper E think about X and Y when given access to T? Well, from its point of view, X and Y conditioned on T appear to be like a uniform chosen bit or secret one, right? So in a sense, E, or the adversary E, perceives that there is a correlation between X and Y. And this is weird because truly we know that there is no such correlation between X and Y. X and Y conditioned on T are uncorrelated. And in fact, for every fixing of T, X and Y are a product distribution. Okay? Now, clearly what's happening here is a computational phenomenon. Okay? And we refer to this phenomena as computational correlation. Now, the tension between the computational aspect in which there is a perceived correlation and the information theoretical aspect where there is no such correlation is the focal point of this discussion. Okay? So now, after defining this, giving this example, I'm going to define a different, completely different kind of protocols, which I'm going to claim or show that they are uninteresting whatsoever. Okay? So here's the definition. We said that the protocol pi is uncorrelated if there exists a decorrelator, which is a polytime machine, such that on input T, transcript T, it outputs two numbers, PA and PB. And now if I were to sample X prime, or independently sample, sorry, X prime from UPA and Y prime from UPB, and by this notation I mean that X prime is one with the probability PA, and the same for Y prime, then what we will get here is that the real distribution and the simulated one are computationally indistinguishable. Now, let me go over that one more time. A decorrelator is a polytime machine that on input when it receives transcript as input, it outputs a description of a probability space. Now, this probability space is, of course, a product distribution. Okay? Now, first of all, note here that X prime, Y prime, T is not really that of isn't really interesting at all. Well, from a cryptography standpoint, at least. Because any eavesdropper that has access to T can, of course, run this decorrelator. And as such, it completely understands how this probability space is created. And even more than that, this probability space is trivial in the sense that it doesn't really require any real communication. One can only needs T, and each party will only can sample its output independently. So there is no real, let's say, interaction between Alice and Bob. So this also means that we can't hope to get any real or any non-trivial primitives using this triplet, X prime, Y prime, T, the simulated one. And this also means, by the indistinguishability, that the real distribution wasn't that interesting at all. So, as I said a moment ago, such protocols, of course, can be transformed into a key agreement, for example. Okay? Now, note here that by this point, we've seen two different kinds of protocols. On the one hand, we have key agreement protocols, which, of course, are non-trivial and interesting objects. On the other hand, we've seen a very uninteresting kind of protocols, which we refer to as uncorrelated protocols. Okay. Now, one might initially think that between these two spectrums, there lies a vast majority of objects and classes that are perhaps non-trivial. But our main result, my main dichotomy result, states that this is not so. And so model some caveats and technicalities, which I will explain soon. For every polytime two-party protocol pi, either pi is uncorrelated, meaning that there is a decorrelator, and this distribution and protocol is uninteresting, at least from a cryptography standpoint. But if this is not so, then pi can be transformed to a key group. Now, this means that there is no intermediate concept in between. Either you have a protocol that is completely uninteresting, but if this is not so, then it implies key agreement. Okay. Well, to show why such a result can be useful, I would like to compare it to one of the useful results by Impigliazzo and Luby. Okay. So let me help you all recall the result. And the result is about distributed one-way functions implying one-way functions. So let's go over it. So Impigliazzo and Luby's result is as follows. For every polytime procedure P, either P can be reversed, meaning you can, in polytime, sample a random preimage of it. But if this is not so, then P can be transformed into a one-way function. Now, this result is celebrated mainly for two reasons. The first is it gives a dichotomy, and the same is in our result. And the second is methodological, because it gives us a very easy and robust tool showing that certain primitives imply one-way functions, or at least a vast majority of our primitives imply one-way functions. And to do this, all we need to do now is show that these primitives, or such a primitive, can be reversed. For example, if we had an encryption scheme, by its init properties, you can't reverse it, right? So by this theorem, it immediately implies that such primitives, of course, give one-way functions. So we really believe in this methodological approach, and in a sense, our theorem can be seen as an analog to Impigliazzo and Luby's result, but this time for two-party protocols. Either a protocol gives us a something to work with, which is this decorrelator that is implied by the uncorrelatedness. But if this is not so, then it gives us something even more interesting, which is key agreement. Okay? So in a sense, now in order to show that certain primitives imply one-way function or key agreement, it's now sufficient to show that, as the same in Impigliazzo and Luby, that cannot be reversed and that it's not uncorrelated. Okay? Now, using this methodological approach, we are able to show our application. So I'm not going to go over all the details. I don't have much time. But I will just say that a very straightforward application is we showed that for some simple or non-trivial symmetric differential probability protocols that compute the XOR implied key agreement. And the way we do it is quite simple, is by assuming that there is, the protocol is uncorrelated and reaching a contradiction by the properties of such protocols. Now, the same way, or the same method is applied in a follow-up work by Heitner, Marquez, and Dumry that showed that or let's say non-trivial coin-flipping protocols implied key agreement. And that was a long-standing open question about the complexity of such protocols. Okay. Now, let me now state our theorem result, but this time with the caveats. So as I said a moment ago, we have two caveats. So let me go over our theorem without cheating this time. So what we had a moment ago is that for every polytime two-party pi, either pi is uncorrelated, or pi can be transformed into a key agreement. Okay? Now, the caveats is as follows. Either pi is uncorrelated on infinitely many k's, or pi can be transformed to a key agreement on infinitely many k's. Now, why we should have expected this notion of infinitely often to arise. For example, you can think about a protocol that on odd choices of the security parameter is uninteresting, but on even choices of the security parameter is a key agreement. We could have expected only to get it once, not twice as we have in our theorem. So this is a caveat, but it doesn't bother us that much. The second caveat is quite more bothering, and it's about row indistinguishability. So we said that the real and simulated triplets are row indistinguishable if any other PPT can't distinguish with advantage greater than the row. And our theorem is that for every constant row greater than 0, pi is row uncorrelated, or pi can be transformed to a key agreement. So the caveat here is that we don't get a negligible row. And this is indeed quite annoying, but I will point out here that the key agreement we do receive in our theorem is a full-fledged key agreement with negligible leakage and as such. And we do this by using amplification results, and this even gives clue in how we are able to get clean results in our applications. Okay, so one thing more to point out here is that decorrelator is allowed to be randomized. So we ask for something quite stronger, is that the real and distributed simulated distributions are indistinguishable even when we add the randomness. Okay. So now I want to speak with the time left about how we prove our theorem. Okay. So in a sense, we need to develop some machinery to argue about this notion of computational correlation. Okay. So we are interested in how a triplet x, y, and t appear to any efficient eavesdropper that only has access to t. Okay. And in this machinery that I'm speaking about is what we refer to as simulators. And let me give a definition. We say that for a protocol pi and rho, a polytime machine sim is a raw simulator for pi if on input t, transcript t, it outputs two bits, x prime and y prime. And now we need that the real distribution and the simulated distribution are indistinguishable. Now, point here that this result is useful because, in a sense, so let me start this. So our result states that for every rho and protocol pi, there exists a rho simulator for pi. Okay. So note here that this result can be useful because, in a sense, the simulating or simulator is able to represent the best understanding of all PPTs. Or in a sense, it can be a representative to any or all that is possible to understand in polytime. And this is quite surprising. Now, using this result, we are able to show, using this representative, the simulated distribution, we are able to give our dichotomy. And I'm not really going to talk a lot about it, but I will just say that, note here that a decorrelator is essentially a simulator that always outputs a product distribution. Okay? And in fact, in our work, we showed that if this is not so, if the simulator doesn't always output a product distribution, then we are able to take this simulator and a protocol and use them to get a full-fledged key agreement protocol. Okay? Now, as I said a moment ago, there are two caveats. The first is computational indistinguishability. And again, here we mean that this theorem only holds for any constant rho, but not negligible. And the second caveat is that the indistinguishability only holds for an infinite subset of cases. And indeed, the caveats we get in our dichotomy result are inherited from here. Okay. So to give a perspective about how we're able, how we achieve our result, or sorry, let me give a perspective and compare it to different results. Well, it's similar in spirit to the so-called leakage simulation lemma. And this is a well-studied issue and involves simulating, let's say, auxiliary inputs. But the results, while the results are similar in spirit, they aren't really comparable. For example, in the leakage simulation lemma, we know that they can, of course, get rid of these two caveats. They don't have these two caveats. And for some of their application, this is quite crucial. And one thing to point out that is to our advantage is that the simulator and the distinguisher belong to the same family of classes, or complexity class. So our simulators and distinguisher both belong to the PPT class. And this is quite crucial to our application, or to our dichotomy. And in the leakage simulation lemma, they always demand that the simulator be of higher class or higher complexity class than the distinguishing class. Now, with the time I have left, I want to speak a little about how we prove our dichotomy result. So let me reallocate our theorem up here. And let me try to state it as follows. So here's a high-level proof. We're going to hold a competition between all PPT potential forecasters, simulators. So in a higher level, or less abstractly, we're going to attach a price such that we incentivize every simulator to output xy conditioned on t when the simulator is given access to t. So in a sense, we want to give this to attach a price that is the best whenever the simulator really does his job and is able to simulate the real distribution. And in fact, our theory, we show that there exists a winner in a sense that it has the best price. Now, both our caveats come from this theorem, or in this stage. Both the row indistinguishability being only constant and the infinitely often, both of these two caveats come from this setup. And it's interesting to see if we are able to deal with this or able to get rid of these two caveats. And this is indeed one of the open questions. And now we have, so by this point we have a candidate that we know that has the best price. So it remains to show that this simulated distribution is indeed computationally indistinguishable from the real distribution. So after we hold our competition, we have now a candidate, and this candidate gives a simulated distribution. And we show that if there exists a distinguisher D that is able to distinguish between the real and the simulated distributions, then this distinguisher can be used to improve our simulator. So using our simulator, using the distinguisher and the simulator, we are able to get a better simulator with a better price, or sufficiently better price. And this, of course, is a contradiction, since by our previous argument, we showed that the simulator, SimHat, was the best simulator. Okay. Now, we'll state here that the part when we showed that there exists a winner is kind of non-black box. So it's interesting to see if we are able to extend, or if this is useful indeed, or it can be used for other applications. And that's about it, what I was going to talk about. So let me now try to conclude. So conclusions of problems. So let me leave you with our informal theorem, at least. So for every polytime two-party protocol pi, either pi is uncorrelated, or pi can be transformed to a key agreement. Again, this means that there is no intermediate concept in between. Either a protocol is uninteresting, or can be simulated trivially. But if this is not so, then it implies key agreement. And as I stated a moment ago, this is useful because it gives a methodological approach to showing that certain primitives imply key agreement. And our theorem can be seen as an analog to Impigliazzo and Luby's result about one-way functions. Now, as for open problems, of course, we really, really like to get rid of these two caveats, but we're not that optimistic. We'll see. And of course, by that I mean that we should get a negligible distinguished probability, and this will really strengthen our result. And the second caveat is to only get one infinitely often. Now, one more open question is perhaps we can find additional application for this dichotomy. And the last question I will talk about is, can we give a similar classification, but this time not for key agreement, but for oblivious transfer? By that I mean that can we provide an abstraction to what it means to have a protocol that is trivial in a sense? Now, in our key agreement protocol, when we said the protocol was trivial, we meant that it can be simulated with no real interaction. So here, if we want to do the same for oblivious transfer, we will require something more advanced, perhaps allow some key agreement. But this is interesting to see if we are able to do something in the same spirit and give a dichotomy this time for oblivious transfer. So that's it. Thank you very much. Actually, no, I'm not sure. So I'll need to think about it. If you want to go, we can try to discuss that. So I'm not sure. Any other questions? But I will state one thing, that the protocol itself doesn't really need to be efficient. So our dichotomy result or our simulator result holds even when the protocol itself is not efficient at all. Okay. Yes.
So the protocols that we know that are kind of interesting from a cryptographic perspective based on abelian functions, zero knowledge proofs.
Yes.
How do they follow this?
So in a sense, I think that the real problem here is that we only get Ron distinguishability for a constant. And for example, the leaked simulation lemma, which I referred to a moment ago, is able to give or to show some application for, let's say, for zero knowledge proofs and such, because they have negligible error. But because we have only any constant error, we think that this is quite a problem, but we're not sure that. So it may be that we are able to do or find some applications, but we're not quite sure. Okay. Any other question?
Thank you.
Thank you.